What if we could trick cancer cells into self-destructing? And better yet, what if we could do this while ensuring healthy cells survive unaffected? Perhaps it seems a bit of a lofty goal because by now we know nothing's ever that simple, because if it were, I wouldn't be here at Brown University getting my PhD in cancer biology. The truth is, I have found that destroying cancer cells is really easy. You could forget to put them back in the incubator overnight or add 10 times higher dose of a drug than you intended, and just like that, I can say I've cured cancer many times on a plastic dish. But all jokes aside, I do take my research as a cancer pathobiologist very seriously. When I was 12 years old, I came home from school one day to the devastating news that my older sister had been diagnosed with a rare and aggressive cancer, synovial sarcoma. After undergoing major surgeries, chemotherapy, and radiation over the course of 2 years, I'm very relieved to say that she survived. However, at the same time, at such a young age, I also saw many families who did not get to take their loved ones home, and I knew that's something that needed to change. As I pursued higher education, I made it part of my personal mission to be someone that contributes to our understanding of cancer, to develop better therapies, and help more families stay together like mine. Here at Brown University, my research is focused on investigating kidney cancer. Kidney cancer is a top 10 cancer in the United States that affects over 80,000 patients every year and contributes to 14,000 deaths annually. Unfortunately, we also see that the number of cases continues to rise at a steady rate. Unfortunately, the challenge with kidney cancer is that it's difficult to detect. It's quite asymptomatic. We do not currently have a screening program, and unfortunately, in most cases, it's caught incidentally on imaging or scans performed for unrelated reasons. What this means is that up to a third of patients could present with advanced or metastatic disease, which makes it much more difficult to treat as these tumors see increased resistance to therapies. Regrettably, we just don't have the biomarkers yet to develop targeted therapies, but that's something that my research seeks to change. Our focus here has been to establish a pro-tumor protein called PIM-1 as a biomarker and target for kidney cancer. PIM-1 is a jack of all trades in the worst ways. It can promote more tumor growth, invasion, migration, and avoid a really important process in cells called apoptosis. You can think of it as the cell's own self-destruct button, a call telling the cell to shut down for good forever. Notably, PIM-1 has been found to intercept that call, allowing tumor cells to survive. But there is this really cool molecule called TRAIL that can send a death ping straight to cancer cells, and most importantly, it avoids misdialing normal cells. The way this works is that cancer cells will have these unique cell towers that can receive and bind TRAIL, sending that call straight through the cancer cell, instructing it to push the final self-destruct button. What I have found in my investigations is that cancer cells with high PIM-1 levels tend to lack the available cell towers required to receive that call. However, in kidney cancer cells, we can trick them using very low doses of a PIM-1 blocking drug to encourage them to make more cell towers. Interestingly, we can combine this treatment of using very low PIM-1 blockade with a new FDA-approved drug that was discovered over a decade ago in our lab led by Dr. Wafiq Eldiri, ONC201, that promotes more TRAIL. And together, blocking PIM-1 and promoting more TRAIL signal amplifies the amount of times a cell tower can receive that death ping and eliminate more cancer cells efficiently. I have found that this is a novel and exciting way to reduce kidney cancer, and we are currently evaluating this in preclinical models in order to inform future clinical trials and pinpoint a trail for kidney cancer cures. Thank you.